it so that the aisle seats are available for those coming into the room. Every seat will be taken.
Hey folks, let those folks in or move over one or the other. Everybody come over one in the front until they're seated. Leave one on the aisle, please. That'd be great. Thank you.
Ladies and gentlemen, if there's a seat on the inside, please move to it to make the aisle seats available. There are more people looking for seats, trying to fill the house. Thank you.
It's not carbonated. Okay, everybody is getting quiet, so I think it's time to start. We've been really privileged the last few years to
have a few new windows open onto the universe that really make us all very excited. Recent missions discovering extrasolar planets, new techniques have been exploding that whole field. The LIGO gravitational wave direct detection has given us a whole new window on black holes and gravitation. And now this, the first image of a black hole. We know for real now that they exist. We've always known, but we've never seen one. Of course, you can't really see the black hole, but now we see clearly its shadow. You go beyond the event horizon, you're gone, and that's it. And this is the first time we've ever seen this, and the whole world has been totally transfixed by this picture. We're really fortunate here in Cambridge to have, as I called it, a centroid of the community here. We have lots of the participants locally based, and fortunately we've been able to have convince them to come down to the Media Lab, so close to this great discovery, to share their insights with us. So it's a real privilege to host this event. We're going to have a panel at the end. So the speakers will come up and give different kinds of insights into the project and into their achievement, into their techniques, and then we'll all come up here afterward, and I'll start off with some questions, and then we'll open up to the audience. So this should be an informative and stimulating and wonderful time. So Michael is going to introduce the speakers. He's the first speaker, but I'll introduce him, and then we'll go from there. Michael Johnson is an astrophysicist at the Center for Astrophysics at Harvard and Smithsonian. He received BS degrees in mathematics and physics from the University of Southern California and a PhD in physics from UCSB, where he studied pulsars and interstellar scattering. Michael joined the Event Horizon Telescope in 2013 and currently leads the EHT Imaging Working Group. In 2018, he was awarded the Secretary's Research Award from the Smithsonian for his work developing new algorithms to reconstruct movies from interferometric data. He has contributed broadly across the EHT project, from imaging methods to magnetic field polarimetry to the scattering and time evolution of black holes. So, Michael, you can start us off.
Welcome, everyone. 2 days ago, the Event Horizon Telescope released this image, and this really is the first ever picture of a black hole. And MIT has played an absolutely foundational role in getting us to this point, and so we just wanted to come share with you the excitement of this moment and tell you about the role of MIT in making it possible. So first, we'll hear from Vincent Fish. Vincent is an MIT graduate, MIT PhD, and he's now a research scientist at MIT Haystack Observatory. And so Vincent will tell us about how the instrument was created, how observations are mounted, and how each year we're making the instrument better to get sharper and sharper images of this black hole. After that, we'll hear from Lindy Blackburn, another MIT PhD, and Lindy will tell us about how the data are processed. These are huge data volumes, petabytes of data, that are reduced down to make this final image. And so Lindy led the team that did all of that data reduction, and we'll hear about that process. And after that, I'll tell you how we turn that data into a picture and what it means. So, Vincent.
Thanks a lot. So we're very fortunate that nature has given us a coincidence of sorts, in that when you look at M87, for instance, and you look at what is the size of the shadow, what is the size of the photon ring in M87, you can work out that it should be about 40 microarc seconds or so, which is an impossibly small angular resolution to have to get down to. But then you look at what is the largest array that you can field from the surface of the Earth, and if you go to the shortest wavelength that you can at the time, which is 1.3 millimeters, you find that you actually get an angular resolution that is sufficient to make that image. So there are a number of coincidences here. One is that, another is that when you look at M87, for instance, at longer wavelengths, you see quite a large jet, and as you zoom in, as you go down to smaller and smaller wavelengths, higher and higher frequencies, you really start zooming in. So nature has been kind to us. So I'd like to spend a moment just talking about the basics of interferometry. Interferometry gets a reputation for being very difficult, and there are technical challenges to it. But in principle, it's very simple. Many of you will be familiar from an optics class or from using an optical telescope that if you have a parabolic mirror, then all of the rays get focused to a point, all the rays on a parallel incoming wavefront. And that's just due to the geometry of the problem. The optical path lengths are the same, no matter what ray you choose. And that's true also if you remove segments from a mirror. As long as those segments are on a paraboloid, everything will come together in focus. Now, of course, you lose out. Some of your photons fall through the mirror, and the image that you make at the end won't be quite as good, but the way that it's not as good is highly predictable, and you can compensate for it. Now, if you were to take those segments and not keep them on a paraboloid, but put them on the surface of the Earth, of course, they wouldn't focus anymore. But if you can accurately time tag your data, and if you can record both the amplitude and phase of the data, then you can reconstruct the telescope as though you were able to have a gigantic paraboloid again. So in this case, for very long baseline interferometry, you're looking at some distant object, and by the time the radiation gets to you, you can talk about planar wavefronts, and there is a geometric delay that your signal will get to one of your telescopes before the other, and that's entirely predictable from where you're looking in the sky, where your telescopes are, what time it is. And you can take that out and you can combine the signals. And now your angular resolution is approximately the wavelength divided by the baseline between the telescopes. So you're not talking about meters for a diameter of a telescope anymore. You're talking about thousands of kilometers. And to this day, very long baseline interferometry at millimeter wavelengths gives you the finest angular resolution of all of the electromagnetic techniques. Now, it's not easy to do this. The telescopes that we use are on top of mountains for reasons, and the reasons are associated with the atmosphere. So the atmosphere wants to absorb the radiation that is coming from the source, and it also wants to emit thermal radiation, noise at you. The plot on the left there shows the atmospheric transmission as a function of frequency, and we're up at 230 gigahertz, so on the left side of that. And this is for 5 millimeters water vapor, which would be considered pretty bad weather for Mauna Kea, but on a cold night in Boston, we're lucky to get down to this. And this is for zenith transmission. So if you're looking low to the horizon, as some of our sources are, then most of your signal gets absorbed, and so you want to be above that. And the atmosphere also scrambles the phase of the radiation that you receive. So as I said, we record complex voltages, so we get amplitudes and phases, but because the atmosphere is introducing this variable path length due to turbulence, little clouds of water vapor going through, on a time scale of seconds, the phase that you think you measure has changed because there's this additional delay. And that means that if you want to detect your source in the first place, you have to detect it quickly. So you need a lot of sensitivity. And so it's expensive to build telescopes, but as I showed a few slides ago, there are millimeter wave observatories already existing in the world, and we can't make them larger. So how do we collect more photons? Well, we've really been pushing toward more bandwidth. Because the more of the frequency range that you're observing, the more photons and more sensitivity you have. The digital revolution has really made this possible. Back in 15 years ago or so, much of radio astronomy was still being done on magnetic tapes with analog electronics for your back end. And that really set a limit on how far you could push technology. But now, thanks to analog to digital converters that are very high speed, FPGAs that can do a lot of processing, hard drives that are growing in capacity, you can get on the COTS curve and really push your bandwidths. And so the curve here in the bottom right shows the recording rate that the best VLBI observations have been able to do over the course of the years. And the EHT has really pushed on this because that's where your sensitivity comes from. Another aspect of that is that some of the telescopes that we use, some of the observatories we use, actually consist of multiple telescopes. And it's much better to combine the signals so that you add all that aperture together into one larger aperture than to have to record the signals from all of those antennas and find your fringes to each of them. So here are two of the phased arrays. The one in the bottom right here is the sub-millimeter array on Hawaii. And the Smithsonian Astrophysical Observatory has built 2 generations of phased array processors for that, which basically means that when you point at an object, you can sum the signals coherently as though you had one larger telescope. Really, the breakthrough for the EHT has been ALMA. MIT Haystack Observatory has led an international collaboration involving many institutes from many countries to phase up dozens of antennas at ALMA, which is at one of the best sites on the planet for millimeter wave astronomy. So you get really dry conditions, you get the equivalent of a 70-meter or 80-meter dish up there, you get very stable conditions, and that can serve as the anchor for the array making it possible to detect to all your other stations, and then you can connect through those detections. After you take the data, we send it back to the correlator. So we have a correlator at MIT Haystack Observatory. There's one at the Max Planck Institute for Radioastronomy in Bonn. And the point of the correlation process is to take those disk packs that we record on and play them back, inserting the appropriate delays to make everything coherent. You just have to do that over and over and over again. You have to do that over large data rates. You have to do that for every pair of antennas in your array. So there's a lot of computation there. So basically, the correlator is acting as the lens or the mirror that brings all of your signals back together for you. And I should point out that if you are interested in seeing a correlator, MIT Haystack Observatory is not far away. We are part of MIT, though we're not here on campus. It's a nice visit, that looks purple to me. So there's an open house at Haystack May 2nd. If you'd like to come out and hear about what we do, see some of the instrumentation, see the correlator, please check out our website and contact us, and we'll reserve you a spot. So once you've taken the data, of course, you have to analyze it, and the data reduction and calibration process is quite complicated. And so I'm going to hand off to Lindy Blackburn, who will tell you a little bit about that.
Okay, thank you, Vincent. I'm Lindy Blackburn. I'm at the Center for Astrophysics. Joined the HT in 2014. Michael was already there, and we were both postdocs working on this project. It's been really wonderful to see it through to the first image. So I'll take a little bit of a step back because I want to cover the story of how we go through this 12 orders of magnitude in data reduction for the HT. It's really an incredible amount of decimating the data down, and you might wonder why that is, and it really owes itself to both the weakness of the signals we're trying to detect and also some of the complexity of things like fitting out atmosphere, where we really need to record sensitively on just seconds to be able to model these effects. So if we begin here with the correlation that was just covered is where we really form the virtual mirror and fundamentally transform the data to a different type, right? It's raw signals from each telescope, and then we're talking about measured correlations between telescopes at correlation. And we can average down, maybe reduce it by a factor of 10 to the 3, 10 to the 4. Calibration is in some way a very similar process where we're also modeling largely what can be considered clock corrections to our data, where we have very high frequency data, 220 gigahertz, so it's very sensitive to the timing of that data. But the essential difference here is that in correlation, we're largely correcting for a priori clock corrections, a very careful and detailed model of the Earth delays, but still a priori and not from the data itself. In calibration, we want to fit those models. We can actually take a chance to look for the data, extract the signals, and we need to build the model and fit it to average the data down more, maybe a factor of 1 million, as much as 1 million. And then we use that data to infer something about the source, like the image. And I purposely put in a pixelated simulated image here, just to emphasize that there are many, many fewer parameters that we can talk about the source versus all of the systematics and such that we need to fit to in the underlying raw data. So that's a story of this process, and I'm going to walk through a little bit, starting from the very beginning. There's very interesting colors here. I've been going to the LMT, taking a break from my usual job about a month out of each year for the last 4 years for commissioning and observing at the LMT, bringing up for VLBI first at 1 millimeter in 2015, and finally in 2018 we brought it up to 64 gigabits per second, which is double what we recorded in 2017. LMT is an amazing site. I had never been up on a mountain before, so for me it was really extraordinary. It's a 50-meter dish. That's a humongous dish, and it's the largest that can operate at 1 millimeter in the world. I don't know if you can see that small dark hole in the middle. That's apex hole where the the signals come through. So for a sense of scale, this is looking out through the apex of the telescope. You don't see the primary, but you see the secondary mirror where the radio waves are reflected, and then they come in through this hole, get bounced off a few more mirrors, get onto the receiver, very small. The antenna is going to be on the order of 1 millimeter also. And throughout this whole process, the telescope is constrained to a very high level of precision. Right? It must be, the path lengths over this entire 50-meter diameter have to be good to a very small fraction of 1 millimeter to be able to coherently add the signals together just at this one telescope. So that's why there aren't too many of these telescopes around the world, and why the LMT, being the largest of it, is quite complicated to operate. Oh, I didn't mention this. This is a large millimeter telescope. It's in central Mexico. Quite a nice place to go visit. It's an extraordinary site. This is Daniel Palumbo. He joined me in early 2018. He was an MIT physics undergrad at that time. Helped commission the site in that year. Now he's with us at Harvard as a graduate student with the project. And this is a picture of another back-end setup, like what you saw from Vincent. This is down converting the signal and digitizing it and recording it to disks. So this is sort of the process. It's rather extraordinary. We can do most of our processing just using a 2-bit, 4-level representation of the signal, Nyquist sampled. So you see these little dots on the bottom. That's what we're recording onto disk from the original sky signal. And that's what's correlated, and from which we derive our images are just those 4 levels of random noise, essentially. They're saved to hard drives. I might not need to introduce Katie Bauman to you, but she is also an MIT graduate student and then was in our working with us shortly. She's actually been with the project longer than I have, so she joined really early. But she's also come with me for the last few years to the LMT for observing there and helping with the setup. So this is a picture of about half a petabyte of data from that one site, and it gets combined with all the sites, forming the several petabyte data set you might have heard about. Vincent told you a lot about the correlator. This is where the signals are combined, and so this is a fundamental process. Correlation is, in principle, very simple, right? This is a correlation coefficient equation you can get on Wikipedia. It's just you multiply 2 signals, you average them together. Here it's normalized by the noise power in those signals. So in our case, we have, I only drew 6 stations here. We have 8 stations in 2017. And then we measure the correlation across all pairs of antennas. One of the important details is that R, the correlation coefficient, is very small. It's something like less than 10 to the minus 4, maybe 10 to the minus 6. So what that means is you need to average billions of samples to actually extract something out of your noise here. And so the key is how can you average those billions of samples? And one of the things that makes that difficult is that each telescope is subject to its own special systematics. So here I tried to represent some atmospheric turbulence. But the radio waves are propagating through the atmosphere, and they have some unknown delay, equivalently unknown phase. That's actually varying pretty rapidly with time. And this shows you just, it creates on the signal something that can be interpreted as a complex gain factor. This is changing the amplitude of the signal, making it smaller most likely, and changing the phase of the signal. So giving you a little bit of ignorance about exactly the timing of that signal at that one site. And that means that you can't average longer than than that gain is stable. So that's why we need to model these G parameters before averaging the data down to something sufficient to make imaging practical. Well, I'll just go back. One more thing. I mean, it's a difficult problem, but really, what really saves us for VLBI is that you see that this G factor, it affects each station individually. That means there are something like on the order of the number of stations. That's how complicated this problem is. As we add stations to the array, you can see the number of measurements we get grows as the squared number of stations, right? That's how many pairs of stations there are. So eventually you add enough stations and this becomes an over-constrained problem. Calibration becomes much more, maybe not easier, but you become much more confident in it. And we can play this game and try to fit all these things out and get our data at the end. All right, so moving a little bit on to 2017. In 2017, we've done a lot of things for the first time. We brought the EHT to its, say, first generation complete array where we think we can make images of 1 millimeter for the first time. We introduced ALMA. The character of the data changed a lot from previous commissioning years and early science observations. And we did want to be very careful about how we process this data, knowing that it would receive a lot of scrutiny at the end of the day. So we developed 3 reduction pipelines. They operated more or less independently on the data. They used different underlying software, HOPS here, that I've worked on. HOPS stands for Haystack Observatory Post-Processing System. And then Picard, designed by Michael Janssen at Radboud, based on CASA, which is a very powerful radio astronomy and reduction suite, and APES, which is also a classical reduction suite from NRAO. And I'm not going to explain all these little boxes here, but essentially they're building out this clock and phase model as the data are processed and as things can be solved for more precisely until you get a pretty good model at the end and you can create this output data set. So we had these 3 operating independently. This is just an example of atmospheric phase because it's so important. And also to highlight the fact that having a central anchor station like ALMA is extremely useful for this process. With ALMA can essentially phase lock the array because it provides such a high signal to noise to the other sites. And that not only benefits measurements to ALMA, which are relatively easy, but measurements between those other sites, which can be hard, can be challenging, especially in bad weather. So this shows something you can get before or after you've phase stabilized with ALMA, showing just how the strength of the coherently averaged signal over the course of, say, a several-minute scan becomes stronger, much more stable. We get a much cleaner measurement after we can phase lock the array, entire array with the ALMA phased array. So we've generated this data. There's also an extensive amount of cross comparisons and validation. I mean, this is one of the major reasons we had the 3 pipelines in the first place. We also have different ways of splitting up our data in time and frequency, and we check self-consistency. So these are just histograms of representing self-consistency of the data across pipelines, and in this particular case, things are fairly consistent with their statistical errors, so the thermal noise. And that's really where we want to be. It's not always the case. We expect some residual systematics, in which case we fit those. They're about a degree in phase, about a 1% amplitude. So we know that those systematics become, after we fit everything out so far, the residual systematics that we're passing down to imaging, those become important when the signal to noise of our measurements gets beyond 100 or so. So one important sort of independent piece of information we have, I haven't covered it all, and it's not really relevant to the decimation of the data, but that's our independent estimate of station sensitivities. So we call this a priori calibration, flux calibration. This is done at the telescopes. Each telescope has some idea of how much collecting area it has, some idea of how much noise it's subject to from the atmosphere and the receiver. And this is information that's very hard to really pin down precisely because you don't have a good, you just have one little antenna, the signal's very weak. You don't get quite the clean measurement you do from correlating data across 2 different sites. But we do want to bring this information in. It's hard because we have, we've built up all these different telescopes built by different people and of all different types around the world, and trying to combine this into a systematized way of characterizing their sensitivity is quite complicated. This huge effort was coordinated by 2 Radboud graduate students from the Netherlands, Sarah Sohn and Michael Janssen, so I wanted to highlight their work here. So one of the reasons it's important is before that, the correlation coefficients we measure, they're really in units of noise of the telescopes. They're not in something we can directly interpret as flux, correlated flux on the sky. But once we know how much, what is an intrinsic sensitivity, we can then bring that onto a physically relevant scale. So this plot just shows the building of the data. You might probably know about Earth rotation, aperture synthesis now. Michael will probably talk about it more later. We're measuring spatial frequencies on the sky. You can see how those frequencies are built up over time or over the night. But on the right here is really what I wanted to show, which is our calibrated visibilities. On the x-axis is the baseline length. So we've projected what's a 2D thing onto just this 1D representation of baseline length. But what you can see here is that this it's remarkably simple, and we were extremely happy once we saw this. Right? It tells you that even though we've looked at all sorts of orientations, the profile here is fairly similar for different baselines of the different colors. And this isn't a formal fit to the data or anything, but this is just what you would expect for the flux density. How similar the signals are versus baseline length. It's just a simple model. It's just a thin ring on the sky, perfectly symmetric. And you see this nice bounce. And so this is tantalizing evidence that something like a ring would be a very good fit for our data once we go through the entire data processing and analysis and imaging pathway. Finally, there's another interesting thing that can be seen just in the raw data itself. And this is using something that we call closure phase. It's a little complicated, but essentially if we're summing the baseline phases of a closed triangle and array. And as you can see from the deltas, this is supposed to represent the extra propagation delay or something from the atmosphere over each station. You can see that if you sum it out over a closed loop here, those cancel. So you're left with only the closure phase that is imparted from the source. So that's a very nice quantity to have. You don't need to model anything about the atmosphere to actually get this. You just need to be able to calculate this closed loop. And what you see here are closure phases for a variety of triangles. It's going to be hard to see, I think, because of the colors, but we have the 4 days of observations. And Vincent brilliantly scheduled these observations, so we have 2 days in the beginning, which are right next to each other, 2 days at the end, which are right next to each other, but a few days in between. And what we see is on some triangles, there's a dramatic difference in closure phase between those first 2 days and the last 2 days. While within those 2 days that are right next to each other, we see pretty self-consistent closure phases. So this is really interesting. It tells us that the compact structure is evolving over those 4 days. It's not unexpected. It's not unbelievable. For a 7 billion solar mass black hole, it's on the order of the dynamical timescale. But it really gives us the exciting possibility that we could eventually make movies of this kind of evolving structure over time. If we cadence our observations correctly. So this is where the data story ends. I'll leave it to Michael to really show you how the imaging is done and what the science we can extract is.
Great. OK, so before we dive into imaging, I just want to give you a sense of why this was such a tricky problem for us. So we're trying to make a picture of something that no one has ever seen before. We're trying to do this with data that's extremely difficult to calibrate. And we're doing this with an instrument that no one's ever used before. Okay, so we're pointing up at the sky, and we're we're looking with new eyes. There's nothing we can look at and say, oh yeah, that looks like what these other people got. So our instrument must be okay. Or oh yeah, that looks like what we got last year. It must be okay. Right? Everything is for the first time, and so it's this incredible challenge of how do you develop confidence in a result in this environment. And how can you develop confidence in something so profoundly new as a picture of a black hole? So that's what I want to walk you through a little bit. So the first thing that we decided to do was that we were going to break our imaging up into 4 separate teams. So we said, before we do any imaging at all, we're going to divide up the data that Lindy sends us. And at this point, this is data that can just be emailed. It's a very small amount of data. So it's divided up among 4 teams, and we said we want them each to make images blindly. Okay, and this isn't just an imaging algorithm that's blind. It's actually the entire process of considering what the data are telling us. So some groups might say, oh, I think this station has really poor performance. And other groups might say, I think that station's fine, and that those are data properties of the source. Another group might say, we're going to flag that data out. We're not even going to touch it because we think it's contaminating the results. And another group might say, well, we think we can calibrate it in a particular way. Each group picks its own algorithms. Each group picked its own choices. So we got the data, and we spent 7 weeks with no communication at all among these 4 teams. And then we got together at a workshop, and we compared the first images that the teams produced. And I'm so delighted to share with you the first images ever with our new plum color map that no one has ever seen before. It's actually quite striking. We actually spent months discussing this. How do you visualize these images? There's no color in our images. It's just brightness. So actually, the most sort of faithful way to show it is just on grayscale. And so we went to great trouble to make things perceptually uniform and all these things. And it's striking to see how different the images look when you recolorize them. In any case, so we came together. The 4 teams revealed their results, and we saw each team had reconstructed a ring. They all had about the same size, and they were all brighter in the bottom. And that's when we knew we really nailed this thing. We knew that there was an image of a black hole in the sky, and all we had to do was turn this into a final image to refine the algorithms. This is a picture of the first imaging workshop. Enlightening. And that is the first image of a black hole. And I just wanted to highlight a few of the key contributors here. Andrew Shale and Kazu Akiyama both developed imaging libraries as graduate students. So Kazu is now a postdoc at MIT Haystack, and Andrew's just finishing his PhD at Harvard. But we used 3 different imaging techniques in our final results. And these 2 members wrote the software. They led the development of the software for 2 of them. It's really incredible work. In addition to that, Daniel Palumbo, you've seen before, and you'll see a lot of familiar faces in here, including Lindy. It's a small project. We all kind of do everything, and it's just a huge amount of fun. Shep Doleman is the director of the project. He was at MIT Haystack for a very long time and was the assistant director there. He's now at the Center for Astrophysics. Katie Bowman is an MIT graduate from CSAIL who's had a huge role in these results. And we even got some new friends along the way. So Peter Gallison, who's here today, he's Harvard faculty in philosophy, actually, in history of science and physics. And I think he came into this expecting that he was going to make a documentary, but by the time we got to the workshop, he had his sleeves rolled up, a laptop out, and he's working away with the rest of us. Likewise with Ramesh Narayan, a theoretical astrophysicist. There's something just really special about this problem. You have a few hundred measurements, and in those measurements is hiding the picture of a black hole. And it's this really pure mathematical problem of how do I turn my measurements into this picture, and how do I track that and understand what I'm doing. So a lot of people are being captivated by this project. Now, I just want to give you a sense of what it looks like to turn these data into a picture. So at each point, if you have some data, you have 2 goals. You want to make a picture that's consistent with the data you have, and you want to make a picture that's sort of maximally conservative with respect to all the information that you don't have. So this is a snapshot of that video that Lindy showed you. This is just one baseline on the Earth joining those 2 stars. And in the center, that's the baseline coverage you have. So the points are the information you have, and where there aren't points is all of the unknown. Right? There's this desert of unknown that you're just sampling a few points in. So in this particular case, if we take our imaging algorithms, what we get with just this one baseline is just a big blob on the sky. We're basically sampling one spatial mode on the sky. We know how much power is there, so that tells us how big this thing is, and we don't get anything more. Now we add a second baseline. The second baseline adds some more information at different modes. It adds a little bit of high frequency information. And so that breaks this blob symmetry. It tells us that there has to be some small scale structure in the image. And you see that it splits and it starts to become more intricate. Now we add a 4th site, and now we have 6 baselines. As Lindy said, this grows roughly with the square of the number of baselines, n times n minus 1 over 2. So it grows rapidly as you add more and more sites. And so it's the type of project where you sort of have nothing, 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 and then all of a sudden, boom, you have an image. And it's really exciting, just to see where is that point. And for us, that was in 2017. So here, now you can see we start getting information at different position angles. They're pointed in different directions. Now all of a sudden our image is becoming more intricate. You can see this ring, it's hiding in there, right? So we add one more site in Spain, and then all of a sudden this sharp ring pops out. And so that's the amount of Fourier information. Right? You can mask out almost all of the Fourier plane, but what's left is still enough to get you to that picture of a black hole. What does this mean, though? How do we use this to inform our knowledge of black holes? What does it mean for general relativity? What does it mean for science? Right? And to understand that, you have to understand why a black hole has a ring in the first place. So this animation shows that. It turns out that light propagating near a black hole doesn't follow straight lines. It's curved because the black hole is curving space-time. Light can even wrap around the black hole. It can go in circles around the black hole. So what happens is if you light up the space-time near a black hole, you have lots of photons flying everywhere. The ones that are too close to the black hole or the ones that are pointed at it fall in. The ones that are further away get pulled around it. And the net effect is that the black hole is casting a shadow on that bright surrounding emission that's almost perfectly circular. Okay, so let's say that we want to turn this into a test of general relativity. Well, the first thing we need to know is what's the size of that circle on the sky. It turns out mostly that depends on the black hole's mass. bigger black holes cast bigger shadows. It's just proportional to mass. Now for M87, we have a couple handles on what the mass might be. One is to look at the motion of gas on scales of sort of tens of thousands of Schwarzschild radii, so pretty large compared to the size of the black hole. And these suggested, before the EHT measurements, that the black hole had a mass of about 3.5 billion solar masses. On the other hand, if you look at stars, they also tell you, right, they're zipping around something there. You can't resolve individual stars, but by their bulk motion, you can estimate that the black hole might have a mass of something like 6.6 times 10 to the 9, 6.6 billion times the mass of the sun. These are enormous numbers. So the other thing is, these are very large-scale measurements. There's nothing to say that there's not something in nature that pops up and prevents a black hole from forming somewhere between these huge range of scales that you're probing, something like a factor of 10 to the 4 from the scales where you're actually sampling what's living inside some sphere, and you're actually seeing it directly. So you might expect that the stellar orbits, 6 billion solar masses, a black hole might actually live there, and it could have less mass than that, and other stuff could be distributed, but it couldn't have more, or you'd see the orbits reflect that. So if there was a black hole, and it had all the mass that you expect from the stars, and the black hole isn't spinning, that's the size you'd see on the sky. Now it turns out if the black hole is spinning, it makes it a little bit smaller. So that's the size of the shadow for a maximally spinning black hole with the 6.6 billion solar masses. And so this little range in between those two, which isn't much of a range, that tells you the range expected for canonical GR. That's if Einstein's right and black holes behave in the way that we think they do. Now, if instead the black hole has the 3.5 times 10 to the 9 solar masses, then you get a smaller ring. Okay, so easy check. We can see whether one or the other of these is correct. But just for fun, what about other things? So it turns out wormholes. It could be a wormhole in the middle of M87. Who's to say it couldn't? And it turns out that wormholes have a smaller shadow than black holes. So here's the size of a wormhole if the mass is the 6.6 times 10 to the 9 solar masses. Let's push beyond that. What if it's something exotic in GR, but there's no event horizon? What if it's a naked singularity? Okay, so it's a singularity in space-time, but it's not shrouded by an event horizon around it. And it turns out that those cast a different shadow still, a much smaller shadow. So we have all these predictions for what the shadow might look like, and then we can sit the EHT image on top of those, and you instantly rule out all of these exotic possibilities. And you instantly rule out the gas dynamical measurement, and we're left with a stellar dynamical measurement. But more than that, we've said that all of that mass that the stars see is concentrated within a tiny region, within the region where photons would go in circles around the material. So it's really quite a stunning confirmation of GR. Our results are perfectly consistent with the predictions of GR. But we can push beyond this. So this is the image we see, but we think that lying beneath it is a much more complicated system, and we're limited by the resolution of our array. And we think this system is alive. It's an intensely dynamical cauldron of hot gas that's hundreds of billions of degrees that's spinning around this black hole. Now, some of this gas gets pulled in, it goes through the event horizon. Some of it flies out on jets. And what we think now is that the black hole is the driver of all of that dynamical activity. Now, this is happening fast. So this is a black hole big enough to engulf our entire solar system. But this black hole, we would see it evolve on timescales of days. So in this particular simulation, 1 second corresponds to 2 weeks in real time. So that's what Lindy said. We see in our data, we don't even need images. We see that the system is evolving before our eyes during an observation. And what can we do with that? So I think we have this interesting preview if you go to 7 millimeters. So this is a little bit longer wavelength, and it turns out that the jet isn't translucent at that wavelength. When you look at it, you're not actually peering all the way down to the black hole. So the jet is opaque, and you see this beautiful extended jet, and you take observations over many months, and you can patch them together, and you see that this jet is alive, and it's writhing. And the black hole is expelling huge amounts of energy that are just rippling down the length of this jet. And that's the EHT image, and you can see the size of it when superimposed on this image, which is one of the highest resolution images of M87 ever made before the EHT. So what we know now is that the black hole really is lying at the heart of that system. And what's most interesting is that the EHT simulations that we have, these numerical simulations that are consistent with the EHT results, suggest that the energy in the jet is actually not coming from the material that's falling on the black hole. It's coming from the black hole itself. Once matter falls into a black hole, it's gone forever. You can't get that back. But it turns out that if a black hole is spinning, you can slow it down and pull the rotational energy from the black hole. So if there are magnetic fields threading the black hole, it drags them along with it, and it winds them up like a motor. And that's exactly what we think is happening in this jet, and it's expelling huge amounts of energy. If the black hole in M87 is spinning rapidly, it has enough energy that you could extract to power 1 billion suns for the age of the universe. So this is an incredibly powerful engine, and we're just getting started understanding, watching it live and breathe, and understanding the role of the black hole in these systems. So let me just close by saying, this is a huge collaboration. It's just such a joy to be able to share the results with you, and MIT has just been a huge role in this project. So thank you. Yeah.
Great. So I think we're going to evolve into a panel here. So our speakers will be seated. I'm going to kick off with a few questions, and then we'll take questions from the audience. To avoid the glare of the lights, maybe I'll stand here, at least for now. Let's see. Looking at these things and actually seeing them in false color does, really train people that it's not really that color, right? These are radio waves. And you're looking at them at terahertz, but what actually are these photons? Are these hard X-rays or gammas that are gravitationally shifted down?
So these are actually radio waves being emitted by synchrotron radiation. So these are electrons that are gyrating very rapidly around magnetic field lines. And they're sending out broadband. They're not emitting lines. They're just sending out swaths of energy across huge wavelengths. And the redshift of these electrons that are actually emitting is actually fairly modest. So it's not some huge, it's actually X-rays, but they're redshifted down to radio.
Okay.
Yeah.
And what about Doppler? Because the thing is whipping around. So I would imagine that you're going to see real shifts in frequency depending on what direction they're coming and where they're coming from. But if it's broadband enough, that may not affect your detector. You're just accepting everything. But is Doppler a factor that you have to account for like you would in a regular observation or not here?
Well, it is, but in a different way. So the material that's emitting is moving at a substantial fraction of the speed of light. And relativity predicts that when that happens, the emission gets beamed in a forward cone. And so if you look at the images, they're asymmetric. There's one side that's brighter than the other. And so that tells you that the approaching side of the accretion flow is the bright side. Now, of course, we're seeing this in perspective. The three-dimensional spin vector is pointing out toward us, but not directly at us. It's off to the side at 15 or 20 degrees or so. So it's a little bit complicated to put up there. But you can definitely see that that Doppler effects, combined with relativity, make a big difference.
This is like stellar aberration, essentially, where the whole universe is a point. It's just approaching the speed of light, a blue point in front of you.
Yes.
Yeah, I'll also mention that you mentioned Doppler, and you remember the simulation that Michael showed with the dynamical M87, a very high resolution, is beautiful simulation. And so when those are created, when the ray tracing is done, to actually see what it looks like, that Doppler effect is inverted. And when we sample the emission, it's sampled including all of those effects.
You mentioned increasing resolution. I mean, it's amazing to see this. Everyone wants to see something like the animation at some point. Of course, that's a tremendous challenge. But what actually would the challenges be? Is it Rayleigh? Is it lambda over d? Is it because you have to integrate over days to make this image, so you have motion blur? What are the things that are limiting us, and what do you think we can overcome?
So there are a couple parts of that. These images are diffraction limited, so you can see these circles on them. That tells you the instrument beam, the point spread function. And so you can see that these are actually convolved with that beam. So we're left with only the things that we absolutely trust. So the way to beat that, there are two ways. One is longer baselines. We're thinking about how to push this into space. If you could launch a couple of orbiters, or you could put something on the moon, or you could, there are many things that one can think of that would allow you to push to much higher resolution. There's even an active orbiter called radioastron that observes with baselines that go out to the distance of the moon, just at longer wavelengths. So we know that this is technologically feasible. It's going to happen. It's not going to happen today, but it's going to happen soon. And the second thing that we're doing is we're looking at higher frequencies. So I don't know, Vincent, you want to talk about the recent?
Yeah, well, there is a push toward observing at 345 gigahertz, which is the next atmospheric window. That's a factor of 1.5 higher in frequency, so your angular resolution improves by a factor of 1.5.
Oh, great.
And that's been demonstrated.
Are any space-based missions planned at this point, specific missions, or is this totally on the drawing board?
Well, it's somewhere in between those two. We're working on it.
Yeah. Well, you have some. This will add a little bit of momentum to it.
Well, also, we're not just stuck, right? We haven't filled the Earth. So one thing is the 2017 results. They had this pretty sparse array still. We just had the 5 geographic locations. In 2018, we added Greenland, and we're hoping next year to add another site in France and another in Arizona in Kitt Peak. So this gives us longer baselines, which are very exciting. The image will become sharper. It also gets us short baselines, which are also exciting, because then we might have a chance of seeing the extended jet, and then we'll see how this black hole actually links up with this massive object that actually goes for tens of thousands of light years.
That relates to another thing. When I got the picture, I did what a lot of some of us may have done. I put it into Photoshop and I just pulled the curve, because I saw these hints of ghostly things. And at 45 degrees, you seem to see some hazy, cloudy patch. Is that the beginning of the jet? Is it an artifact, or is it something between the Earth and there? What is this stuff?
Those are artifacts. So this is the limited UV coverage, right? We're just stretching our algorithms to their limit. And we are actually, we can suppress those artificially, but we chose not to. We want to keep a floor that represents the uncertainty in the image and not impose too much of our own will on what it should look like. But that's the kind of stuff that should sharpen. Our dynamic range right now is 10. It's not much. And, yeah.
I'm sure you had a lot of people trying to ask these questions about these things, but I suspected they were artifacts. But we'll see the real extra phenomena soon when you.
Well, make no mistake. We spent months wrestling over these questions.
Yeah, of course.
Yeah. So.
This is the question everybody has asked you, and probably will continue to ask. This is wonderful. You got this big, huge black hole, within range that we can do this. But there are lots of other things. So this Sagittarius A star, which you guys had talked about, that's the one here in the Milky Way. It's not so active. It's not like this. It's flaring all the time. Fortunate for us, perhaps. But we'll be able to see that. How about Cygnus X1? That was the poster child of black holes. It's only 6,000 light years away. Could we try to look at that? Is there a possibility? It's smaller, but it's close. And then there are weird things. This is radio astronomy, not just for black holes, but for any kind of emission. What other kind of things can you look at? People talk about Tabby's star. I don't know if that emits at these wavelengths, but we can maybe see what's causing this really weird, irregular profile from the emission. So what kind of things are you going to look at, or what kind of things can we look at?
So that's really 3 excellent questions. I think we should take those in turn.
We have 3 people.
Sagittarius A star is one of our primary targets. It turns out that it's a harder source to observe because it changes so quickly. So when Michael showed the video of the simulation of M87, you could see that on the timescale of days to weeks, the source structure changes. But each of the images that are up on the screen are from one night of observing. So over the course of a single night, the image is effectively static. Now, for Sagittarius A star, the source changes on the timescale of minutes. You can just point a single dish at it and you can see it flicker. And so if the material is moving around it, then when your baseline is, when you have data from 2 telescopes now, you get a point in the aperture plane, in the UV plane, and then you wait for the Earth to rotate so you get different points. Well, now those are from different images. And so you get a sort of blurring. And Michael has actually led an effort to try to figure out how to do dynamical imaging from sparse data. Do you want to say anything about that?
Well, it's the excitement, right? It's the challenge and the excitement. A day for M87 is a minute for Sag A star. And so we really do have the chance to watch Sag A star evolving before our eyes and to see it. And it's just a computational challenge. We need more information. But we do. We don't want to reconstruct images. We want to reconstruct movies. And we're just scratching the surface of what can be done there. That's where I think a whole new community of scientists can bring a flood of ideas and make this happen.
And how about the smaller black holes that are closer? The CNSX-1 and other sources that may not be black holes.
The angular size of the event horizon is proportional to the mass of the black hole divided by the distance to the black hole. And there are black holes that are a lot closer than the center of the galaxy, but those are stellar mass black holes, so tens of solar masses. And that's a factor of 100,000. And so, if you had one of those sources that was, gosh, a parsec away or less, then you could do that, but that might cause other problems.
These aren't in the sweet spot.
Yeah, so
it's good they aren't.
Yeah, you're not going to get the same sort of angular resolution on them. The third question you asked was on other types of sources, and because the aperture isn't very well filled for very long baseline interferometry. You really need sources that have high, what we call brightness temperature. So effectively, if you had a black body there that were emitting that thermally, how hot would that need to be? And the answer is kind of up around the 10 to the 9 Kelvin range, kind of 1 billion degrees. Shorter baselines, don't require as high of a brightness temperature. So you're really talking primarily about very hot things and non-thermal things. So in addition to active galactic nuclei, you could do this with some astronomical masers. Those are spectral line sources.
Also pulsars.
And pulsars,
yep.
Yeah.
Finally, it's a really exciting time in physics with all these new windows, as I said in the beginning. So, the best is yet to come. But so far, you guys have been confirming Einstein. LIGO confirmed Einstein, and you guys did. And it's amazing, but his shadow looms very far. We have quantum gravity and all these other theories that attempt to push it forward. And it'd be great to see something that points to a new theory, or at least something that can't be easily described, like dark energy or dark matter coming out of this. And CERN, of course, has just verified the Standard Model with the Higgs, which is a great discovery, but there's no new physics. So, what do you think about the signs of new physics? You looked a little bit at, rotating black holes and signatures, but what about anomalies? What kinds of things would you maybe look for, or is there hope we could see one? I guess there's always hope.
Sure, yeah. So it's always interesting to do a test in a completely different regime. So what we're thinking here is it's the first time we have direct evidence and a direct view into a 10 to the 9 scale billion solar mass black hole. The types of tests you can do with this kind of image versus gravitational waves is different. Each is testing some deviation within its own domain. But as you can see, it's a blurry image. We're not going to have a very precise test of GR at this stage, and we'd be very surprised if we thought whatever we can constrain to the 10 or 20% level would really be enough to really pin down some small deviation to the theory.
I also think the crown jewel of this is going to be Sagittarius star. So for M87, we don't see individual stars going around it. We had this roughly factor of 2 uncertainty in the mass. And if we didn't, then our current measurement accuracy might have been good enough to estimate the spin of a black hole, that narrow range of possibilities. Now Sagittarius star is different. It's close to us. We see these stars zipping around it. You've probably seen these movies, these incredible movies, tracing stellar orbits and seeing them just be whipped around by an absolute void. And because of that, we know the mass and distance of Sagittarius star perfectly, to exquisite accuracy. And so if we can extend the EHT and we can really push that, we know that GR breaks down in these regimes, right? It's fundamentally incompatible with quantum mechanics. There has to be new physics living here. I think it's very much a stretch to think that you could see that with this resolution. But with Sagittarius star, there's such a tight prediction for what you would see that I think that's something that over the next few years, as we match these images with our own galactic center, that's going to be really exciting.
Man, you got my hopes up. Hope to see you in Stockholm. Anyway, we have permission to go a little bit longer actually here, so maybe 10, 15 minutes if there are questions from the audience. I'm sure there are. So let's pass the microphone around. Put your hand up if you would like to ask our experts any question. There's got to be somebody here. Oh, there we go.
Hi, thank you. Does the fact that the mass estimate agrees more with for M87, agrees with the stellar estimate rather than the gas estimate, does that mean that all the other black holes, we only know their masses by their gas dynamics, are maybe also off by a factor of 2? Does that matter?
I don't know. I do think that there's a lot of reason to question those now, right? Even our own galactic center, there was sort of a factor of 2 discrepancy, within the last 20 years. And these are not trivial models, right? It's not like you just take, right, for these, to estimate the mass of a black hole, you can just read it with a ruler. There's nothing complicated here. To infer the mass of a black hole on these much larger scales using the dynamics of the gas, that's a much more complex process. So I think this does push, hopefully it will push these communities to develop better models and understand how to, make them more generalizable.
Okay, there's a question down here. Oh, there's one down here.
Roughly speaking, relative to the plane of those images, where does the rotation axis point?
Yeah, so it's really confusing. The jet, you see it going off to the...
The jet is along the rotation axis, yes?
That it is thought that it is, although that doesn't have to be the case. So this jet is actually pointed almost straight at us. It's tilted off about 18 degrees.
And that 18 degrees is enough to make that sharp contrast between the bottom half and the top?
That's right. That's why you only see one side of the jet. The other thing, you see it right at the base, and then it gets accelerated, and so it's pointing away from you. It's this Doppler boosting, so you don't see it. You only see it when it's going slow. But what we know from these images, as Vincent was talking about, they're bright on the bottom. That's where the stuff's coming towards you. So you can imagine that this thing is twisting towards you on the bottom, and it's going away from you on the top. And so this jet is just a little off the line of sight, and the spin vector is pointed away from us.
So if we were to zoom out, we'd see an accretion disk form pretty much around that donut because of the axis is pointing toward us.
But it will be weak, and so you need the dynamic range to be able to image it.
You're not emitting as much there. Is right close to the black hole.
Yeah, so we actually don't know what's causing this emission. It could be the disk, it could be the jet, it could be some part in the middle that's both disk and jet. Yeah. It's this image is dominated entirely by the gravity of the black hole itself, and so that's why increased dynamic range.
It's just electrons being bent as they whip around, essentially. Right?
Well, photons. Yeah.
Photons. Okay. More questions.
As you start putting more of the telescopes onto satellites and putting them in space, and you get outside of the transmission window of the atmosphere, what's the limitation on the frequency you would look at then?
So there isn't necessarily much of a limitation on that, but it depends on the approach that you take. So if you're contemplating a space VLBI mission, you have to ask, do I want to do interferometry just between the satellites in space, or do I want to do space-ground interferometry? And it is a lot cheaper to leverage the large apertures on the ground for your sensitivity than to put large things up in space to provide equal sensitivity. So there is incentive to keep common frequency bands with the ground. But in principle, for space-only baselines, you're pretty much unlimited on frequency.
Well, yeah, so the receiver technology to do the heterodyne things where we're actually recording this full coherent wavefront, that's tough to get up to a terahertz even. But I don't think there are any, there's no reason that couldn't go higher. And a terahertz would already be, that's a factor of 4 higher. At that point, the jet is completely translucent, and you really are just looking right at the horizon.
Yeah, the far side of the moon, I imagine, would be a great place to put an array for you guys. Although it's going to be it's going to steer every month instead of every day.
Yeah, the problem is the time scale, right? You're getting comparable to the time scale of M87, so you're not getting all of this dense sampling on a rapid enough time to make an image. But
yeah, my view on that is that you can make arguments for things out to about geosynchronous or a little bit beyond. Satellites in low Earth orbit whip around so fast that you actually fill in a lot of those missing spacings. And so that's really great for dynamic range and may be essential to make really good movies of Sagittarius A star. When you go out to geosynchronous, now you're getting tracks in the UV plane once a day, which is commensurate with the timescale variability of the M87 and actually of other quasar sources, AGN sources that we observe with the EHT. But if you go too much beyond it, then you're on that month time scale, and your angular resolution is so fine that everything is moving, every source is moving or changing on that angular scale much faster than that time scale. So I think there is a practical limit to that, unless you put up a lot of satellites.
Yeah. Okay, more questions.
So often what we consider to be noise in one era turns into be signal in another. And I'm wondering, is there interesting noise that's on the cutting room floor right now that you'd really like to spend some time with?
So we're certainly not trying to throw any systematics from our source, although it's not crazy. People do try to, for example, average over variability in Sagittarius are not in current data, but people have proposed ways to help stabilize the data to make images at all. But as far as the systematics we're modeling in the data now, there are things like the atmosphere. So if you're interested in that, and we are interested because we're radio astronomers in modeling the atmosphere, we'll pull out the signals, we'll learn something about weather at the sites and how to characterize it.
Any more questions? You guys are quiet. So maybe you're okay. We have Juliana in the foreground.
Building on the discussion about space mission architectures, are you familiar with the OLFAR radio distributed antenna array out of the Netherlands? It's a pico satellite radio antenna array on orbit around the moon. And
it was launched just a year or two ago. Is this the one?
It may still be under development, but
okay. And do you know the wavelength that it's observing?
I don't offhand. I know that the intention is to measure kind of early phenomena in the universe.
I see. Yeah, I think those tend to be at longer wavelengths.
Yeah.
Right. There's a trade-off here. We want to go to high frequencies and get higher resolution, but in doing so, you need much higher surface accuracy for your dishes. So you got to make the dishes smaller. And the receivers are not, they have more noise. And so the whole problem overall is that, there's some sweet spot beside just pushing to the highest frequency you can and still having enough sensitivity to see anything. So this is why, these current space VLBI missions, they're still about a factor of 10 too long in wavelength to be able to peer down to these scales. But I think, absolutely, we want to piggyback with these other efforts and get something off the ground quickly.
What kind of antenna size actually would you want for a space mission? Now, these are big antennas that you're using terrestrially, so could that scale to a smaller one and still be effective? Millimeter wave, technically it's not so much of an issue, but to collect enough radiance, you want a big diameter.
Yeah, well, the bigger the better, but big also makes it very difficult to create in the first place, very expensive on a per element basis. Very small, on the other hand, you don't have the sensitivity. And if you were to consider like phased arrays or something like that, then you would need a receiver per element in the array, and so that becomes cumbersome and expensive as well. I think if you're willing to leverage the big apertures on the ground, not just ALMA, but LMT, phased SMA, phased NOEMA in France, you would be happy if you could get a satellite up there that's 3 meters, 4 meters, 2 meters, so somewhere in that range.
They can be really small and still be tremendously effective.
Yeah. Good. So it's 2:10. If there's no other burning question, I think we can wrap this up and thank these folks for coming down and congratulate them and their collaborators on this great achievement.